we have seen trees. We're supposed to understand how the trees are constructed, and we try to understand that, in fact, in these trees, maybe there are problems of accuracy. Indeed, when we see the way they are constructed, it's a very simple way. These are made of binary splitting. That means that we separate the values of a given covariate into two parts. That means that we only consider one covariate at a time. Intuitively, we can understand that maybe we have some prediction problems, some accuracy problems with these trees. That's the reason why we are going to try here to improve this accuracy through bagging and random forest techniques. The idea of bagging is to construct a large number of trees. We are going to see how to construct a large number of trees in some minutes. But let's imagine first that we are able to get, let's say, B. If we construct B different trees, we could obtain B predicted values for a given set of covariates, for a given input. In that way, that means that we could average these predicted values. And what would be the consequence of averaging these values? It's very simple. That is intuitively, it's clear. We would be in that way able to reduce the variance of the prediction. Indeed, when you average, it is clear, the variance of an average of IID random variables, we know that we get like this. If we make the variance, if we compute the variance of an average of random variables, IID random variables, we get the variance of the random variable divided by the number of data that we have in the average. In this case, we would have B predicted values by B different trees. That means in the case of IID random variables, when we compute the variance of an average, we get the variance of an initial random variable divided by the number of random variables that are involved in the mean. That leads to clearly, mathematically as well, a reduction of the variance, a reduction of the variance, in this case, the variance of the prediction that would be given by a method which uses a large number of trees, let's say. Obviously, that depends on the data, on the predictions, on the predicted values that we have. That depends on the dependency that we have between the random variables. We will see that further, and we will see how to improve that for that point specifically, the dependence between the predicted value. That will be the object of a random forest in some minutes. Okay, but let's keep this idea of, okay, I'm going to construct a large amount of trees, and I'm going to average the predicted values that I have. In that way, I'm going to reduce the variance of my prediction, I would say, of the average of my predictions. Since I'm doing an average, I'm going to decrease the variance of the prediction. This method that we're going to use, this average of trees, is named bagging. Bagging for Bootstrap aggregating. That's the idea. Just average trees. And Bootstrap aggregating, because Bootstrap is the way we are going to use to construct B different trees. Another expected advantage that can be really easily understood is the fact that we are able, by averaging trees, we are able to avoid in some way overfitting. Indeed, we are going to average different values, different predicted values. If we only use one tree, we understand that if the tree possibly overfits, Therefore, it's possible in a way that we model errors with a tree, but now we are going to average them. Therefore, we have more chance to remove, in a way, to mitigate this overfitting. Since we are in this process of averaging, we remove the errors in a way. So that is another expected advantage. This advantage is to say, okay, when we average, we should avoid overfitting. That also means that in the trees, if you remember well, we use the, let's say, complicated method to remove in a single tree. We were trying to avoid overfitting by pruning the trees. That means here that maybe we are able to avoid pruning the trees. That's what we are going to do, because the process of averaging compensates, maybe, we hope, that will compensate this the pruning effect. The objective is the same. When we prune the tree, we avoid overfitting. When we average the trees, we decrease as well overfitting. That means we are not going to do 2 times the same thing. Therefore, maybe if we average very complex trees that overfit, it is possible that we avoid, that we decrease overfitting as well without pruning anything. That's what we are going to try to see. We are going to use Bootstrap. What is Bootstrap? This methodology to construct the different trees. Very simple methodology. We create multiple subsets. We create from the initial samples, we are going to create what we name B Bootstrap samples. B Bootstrap samples of the same size as the size of the initial sample. How is it possible to construct that? Without any problem. Random picking with replacement. We pick up randomly with replacement and data from the initial data set. The result of this is one Bootstrap sample. We do that B times and we have B Bootstrap samples. Okay, we use this technique. With this technique, we are going to be able to construct B trees. B, most of the time, is between 100 and 400. For these trees, I say it once more, we are not going to prune anything. No pruning technique, no stopping criterion. We construct very complex trees, but we are going to average them. Therefore, we are going to smooth this idea of overfitting. We are going to make it disappear only by averaging. That's the idea here. This next, for regression trees, we are going to average the values predicted by all the trees, and we are going to name here fbag. Fbag, this is an estimation. This is an estimate. This is an estimate of the value of the output for a given input x, and it is obtained by averaging all the predicted values for every tree here, f star b of x. This is the predicted value for the tree for x with the b3, the tree which is constructed with the bth bootstrap sample. For classification, it is approximately the same thing. For classification, it's also a mean in a way, because with each tree, we are going to have a winner. At the end of a tree, we have a class which is chosen by the tree in the case of classifications. If we have B trees, therefore we have amounts of times that a class has been selected, and we take the highest amount. That means that the predicted class for a data is taken from the majority vote, the highest number of times that a class has been chosen among the B trees, the majority vote among the classes chosen by each tree. Okay, when we do that, maybe we reduce the variability. It is clear, it's shown that we can reduce the variability of the prediction, but as we said, for the trees, a very positive point of trees is that we have a very nice interpretation in trees. We are able to find a way an output is obtained. Since it depends in a very easy way on the different covariates. We lose this interpretability, and it's a problem. But there are, possibilities to understand the importance of every variable in the predictions. This is beyond the scope of this presentation. There are several plots for that, and I will go back and I will explain that in another video. Now, to introduce random forests, I would say that the trees may have problems. The bagging technique that we have seen up to now may have some problems coming from the fact that maybe, as I said at the beginning, maybe the predictions of different trees may be very dependent. Imagine that there are some covariates that are very important. We can imagine that they appear as very important. They appear very high, at a very high level in the trees. They are very important splitting variables. Therefore, they appear in most of the trees, the trees coming from the Bootstrap samples. And as a result, the predictions given by the different trees may be very dependent. They are very positively correlated. And that could be problematic. That could be problematic for the results, since the objective of bagging is to reduce the variance of the prediction. This objective maybe is not reached because of the fact that the predictions are very dependent. They are positively correlated, and we know from the beginning the variance of a sum, the variance of an average of random variables. Okay, this is the sum of the variances of the different variables divided by the number of variables up to the square. But also, in this formula, the variance of a sum, the variance of an average, let's say, whatever, we also have the covariances between the different variables that appear. And in this case, the covariances between the different predictions obtained by the different trees from the different Bootstrap samples could be very highly positively correlated. Obviously, due to the fact that they are constructed by the same, there is a problem, by the same variables, by the same covariables, by the same factors.